Okay, here we go, folks. Live from Syosset. It's AP Physics Course 1, Lesson 7. Question, how can equilibrium problems be solved with translational and rotational formulas? There should be an S there. Formulas. And basically what I mean by translational and rotational formulas, we're going to be using the fact that if something is in a state of equilibrium, all of the horizontal forces have to balance each other out, and all of the vertical forces have to balance each other out. So we could say the sum of all the forces in the x direction have to equal 0, and the sum of all the forces in the y direction have to equal 0. So those are the translational formulas that we're going to be applying. Now, if it's also in rotational equilibrium, that means you could pick any single point on the object and analyze all the torques about that particular point. And if it's in rotational equilibrium, the sum of all the torques about any particular point, and it's usually a point of your choice, also has to equal 0. Right, right. And basically, it's very important here that, how do I say, the torques, about a point of your choice. Or another way of saying is the torque about any point.
What does that mean about?
You know how, like, if you have an object and you exert a force on it? Well, in order to figure out how much torque is being exerted, you have to ask yourself, which point are you analyzing? Which point are you considering to be the pivot point? So if you were considering this point right here, then the torque would be the force times that perpendicular distance. If you were considering all the different torques about a point over here at the end, then it would be the force times the length of the whole beam distance. So if it's in rotational equilibrium, you can pick any point on that beam, and if you analyze all the torques, they should all balance out. And the torques going clockwise should be equal to the torques going counterclockwise.
So can you say the torque of a point of your choice?
The torques of.
It's the same thing.
Yes.
Okay.
Yes, yes, yes. Yes, yes, yes. You can say the torques of a point of your choice. Yes.
Just like the torques, like of any point, like if we were to add them up, they'd have to like cancel out.
Right. Right. And after we do a couple of examples, I think you're going to catch on. Okay? Ready to rock and roll? We got the question down?
Yeah, buddy.
All right. Hello. Okay. So we have this girl who's going to dive in to the pool, and that kind of reminds me of a passionate project. A student last year, one of her passions was diving. So for her passionate problem, which is a 5-minute oral presentation each of you are going to do at the end of the school year, she brought the whole class down to the gym, and not only did she do a few dives for us, she explained the physics behind the dives. It was a very excellent demonstration.
Oh, wow.
So let's say we're trying to figure out how much this little beam right here, how much this little platform is holding up. What's that upward force? Holding that, because when she dives, the board actually might even bobble on that point right there. So we're trying to find this, and we'll call it a force over here. Now, obviously, the weight of the girl is acting downward. So, let's say she weighs about what? 120 pounds or
Yeah.
120 pounds. So that would be roughly 480 newtons, correct? So Fg of the diver is 480 newtons. And let's say the diving board itself weighs, I don't know, how much do you think the diving board weighs?
I would say 200.
I don't know,
200
really a lot.
pounds. 200 pounds.
No, no,
No,
no.
not that heavy, but like.
I can carry my diving board out
Really?
to the
What?
pool.
No, you got it out of the.
I mean, I could bench 400.
Probably 80 pounds. Probably like 400 newtons, so like 100 pounds.
I'm thinking maybe a big board like that might be 50 pounds, 200 newtons.
Something like that.
You see, this is what I mean. Like,
That's the board. And we're trying to find that supporting force. Now, of course, some of the weight of the diving board is acting over here, pulling down. Some of the weight of the diving board is acting here, pulling down. But some of the weight of the diving board is acting here, pulling down. But we could just simplify the whole shebang problem by letting all of the weight of the diving board act where? At its center. So, right here at the center, does that look like the center?
Yeah.
yeah. It's right under the belt.
Fg of the board. No, I'm just going to say 200 newtons. And how long do you think that diving board is?
About
8 meters. How tall is she?
You know how long that is, Nicole?
What if that person's just really short?
Well, if she's 5 feet tall,
3 meters? Like
I would say
5
10
feet.
feet.
like 2
All right, say
10.
she's 6 feet, so that's roughly
10.
2 yards, right?
I feel like 2.
Which is roughly 2 meters. So that's 2 meters.
Be like
I
4,
say
5,
2.
5
I think
meters.
it's
5.
We'll say 5 meters.
Oh, baby.
Yeah, we'll say 5.
So the length of the whole board is 5 meters. And this little attachment right here, where the beam is actually set on right there, what is that distance from here to the end?
Oh, I could not see that.
Yeah, I didn't see that either till right now.
There.
Oh, yeah. If I erase that there, watch.
There's an attachment.
I see it
There's-
I did not. I was like.
There's like a little pad right there that the board sets upon.
Wow.
Yeah, that's right. Okay. Are there any other forces acting on that diving board? If those were the only 2 forces, would everything be in equilibrium, nice and balanced out?
No.
No.
What would happen?
It would like. It would.
clockwise.
Well, the diver would.
Yeah.
The diver would. The diver would tilt it.
The whole board would
Go like.
tilt like down like that, right?
Yeah.
You know?
So there needs to be a support on that.
So there's got to be support on the other side over here. So guess what? Over here, what's going to be happening at this point here?
Like this downward force.
Yeah, there's going to be a downward force preventing that side from like tipping up. So there's a downward force. That's got to be pushing down on the board over there, and we don't know how much that is.
We don't know FS either, right?
We don't know FS either. I'm going to call this F sub D for down. Very creative, yes? So we don't know F sub D as well. But while she's standing there, concentrating, thinking of the dive, everything is balanced out. That board is obviously not moving, so it's in a state of equilibrium, yes?
Yes.
So we could say that the sum of all of the forces in the x direction has to equal 0. We don't have any forces in the x direction, yes? So that's really not going to apply here. But then we could say, hey, the sum of all the forces in the y direction, they have to equal 0. So we do have vertical forces here, yes? So what's that formula going to look like if we write it out? Dan the man, come on. FD plus what? FG of the board
Plus FS.
plus FG of the diver. Yes, but you know what? Before you do that, I'm going to then just say minus Fs equals 0 so that it's more in line with this right here. The sum of all the forces. And you actually chose down to be the positive direction, but that's fine. It's all good. And you're right, you can take that Fs over to the other side, and that's fine too if you jump right to that. It's all good, Danny, it's all good. So basically all the down forces have to be equal to all the up forces. Or if you want to be sophisticated like me, you could say all the down forces minus all the up forces have to add up to 0. So what do we have here? We have FD down, which we don't know what it is, plus 200 newtons down, plus 480 newtons down, minus Fs up equals 0.
Subtract FS. I mean, add FS, right? And then that's pretty cool.
All right. Now we can't just go ahead and solve because we have two unknowns with the one equation.
Two equations.
So we're going to need to go and use
Some torque.
the, where is it? Whoa.
So that's small.
We're going to have to use this torque equation right here. The sum of all the torques about any point, a point of our choice, would have to also be equal to 0. Now, here's the trick. If you choose a point that has a force going right through it, that particular force is not going to be part of that torque equation.
There's no distance from that point to that force.
Exactly. So
That's a good trick.
we can pick any point we want, and we would just have two equations with two unknowns, but we can make life easier and choose more appropriate points. Anybody want to give a guess of which point to choose?
FS.
Where?
Like the support. Like the thing right there.
Like right here?
FS.
we could definitely choose that point and consider all the torques going about that point. Okay? And would Fs be putting any torque on that point? No. Okay? So that's definitely one we could do. Okay? So why don't we do that? I'll make some room here. Let's see.
Are you supposed to calculate that FD plus 360 newtons minus Fs equals 0?
We can't do too much with that because we have two unknowns.
Yeah.
So
So you can just simplify it, but that doesn't really do anything for us.
yeah, we could simplify it. Oopsie.
Yes, Kai.
So
Excuse me, Kaiser. Do you still have sheep over there? Or is it that? Somewhere in the room.
so we're going to apply the sum of all the torques about this point. We'll call this point right here point P. So all the torques about point P have to equal 0.
Should you always choose a point so one of your like with that has one of your unknowns? So like
That's like the appropriate thing to do. That makes life easier.
okay.
Yes.
Because that way you won't have to like do like elimination or something.
Right.
So technically you could have chosen FD.
Yes.
Okay.
Matter of fact, that's where I was going. This is just good.
Mind.
So why don't we make torques going counterclockwise be positive, and torques going clockwise be negative. Now you know one thing we didn't establish, which, or maybe we did, but did I write it down? We need to know this distance here.
Yeah.
We did not establish that.
So just looking at the overall board is 5 meters.
Maybe like 2 meters.
2 meters.
Maybe 2 meters. So now I go and I write out my torque equation. So we start off with this force right here. We don't know the magnitude of FD, but we could write down how much torque it's going to have about that point. Is it going to be a positive or a negative torque about this point right here?
Positive torque.
Positive, because it's going to make the board go over that way. Whoa, and we established that's going to be positive. So this is going to be positive FD times 2 meters.
Where's your 2 meters?
Right
That's the
here.
distance.
Because if you take the line of action of the force to the pivot point, we need this distance right here. That's the perpendicular distance. And we said down here that that distance is 2 meters.
Oh, like you. It would be given, right?
That's given.
No, this is lost.
It has to be equilibrium. She can't get jumped up.
Now, what about this force here, the support force? Is that going to put a torque on here?
It is not.
It is not, because bam, it's going. It's not going to get any twisting or turning because of that. So that's not going to be part of this equation. So what's next? This downward weight force, the weight of the beam itself, the diving board. So it's going to be 200 newtons. And is that going to put a counterclockwise or a clockwise torque about this point right here? Clockwise. So it's going to be going clockwise, and we said that's going to be negative.
It has to be which side of the pivot point it's on.
So if it's going to pivot about that point,
If it's pushing up or down.
and it's pulling down over here, board to want to tilt like, whoa, that way.
So isn't that positive? Because it's on down is positive.
No, down's negative.
No,
Well,
down
we're
is
not
up,
doing
down's but it
we're
doesn't
not doing
matter.
up or down anymore. We're doing a torque equation,
This is 200 newtons.
and we're doing
That's 200 newtons.
counterclockwise is positive, clockwise is negative. So look, if this was a teeter-totter and it was bounced out right here at that point right there, and you stood right here, which way would you make that board end up tilting?
Down.
Down.
Right,
Clockwise.
it would go clockwise.
I mean,
And about that pivot point, and we established that's going to be negative. So this here is going to
minus
be
2.
minus 200 newtons times, what's the perpendicular distance between that force and P?
Point five.
Well, is that the middle of the board?
Point five.
Oh wait, no, then it's point.
3.
Like
0.5 meters?
But how do you know that?
Because that part's 2 meters, and that's the center of the board. 2.5.
Because we know it's 2.5
Oh, okay.
to here, 2.5 to go all the way out.
You set that equal to 0.
Set what equal to 0?
That.
These two? No, we're not done yet. Because what other torque is acting on it?
The lady.
The torque due to from the weight of the diver there. And now is that torque due to the diver going to be positive or negative?
If it has perpendicular
Negative.
to the pivot point.
Negative.
It
It's going to be
Five.
480 newtons times what's the perpendicular distance from the
5 point.
diver to this pivot point right here?
5.5.
No, it's like
No, it's
like,
three.
let's call it
3 meters.
3, yeah. Because we said the other one was 2, so this has
No,
to be
it's
3.
5 points.
No,
Isn't
has
it
to be
5.5?
5, yeah.
No, because we said
No, it has to be
3.
2.5.
Oh,
It
it's
has
no,
to be.
it's more than 2.5. No. It's 3.
It's 3. She's right.
It is 3. It is 2.5.
Yeah,
It's
'cause
2.5.
5 minus 3 is
Yeah, it
2.
is 3. It's 3.
2 is what this goes.
Wait, no, it's not.
Times
No, I swear
3.
to God,
Right.
it's 3.
It has to be
That's
It's-
2.
From
it's
here to
3.
here,
That's 2.5.
But
That's our pivot point.
But no, to your pivot point is
to the
Oh,
pivot
I thought it
point.
was.
Oh,
I
that's
keep
the
thinking
pivot
5
point.
is the
That's an extra
radius.
0.5.
The pivot point isn't the middle of the board.
And now all of that has to be equal to 0.
Yay.
And now we have two equations with two unknowns, which is solvable. And the good news is we chose, or Alex chose, our second torque point so appropriately that that bottom equation really only has one unknown. So we could solve the bottom one for the downward force and then plug that into the top formula to get the support force. Now, interesting enough, a lot of people look at this problem and they just see like this right here, because this a lot of times is, spelled out. And if you just were looking at this and you see the beam weighs 200 newtons and the girl weighs 480 newtons, looking at that alone, how much would you think that upward support force would have to be?
680.
680 newtons. But it turns out it's going to be even more than that because
There's an FD.
there has to be a downward force over here preventing the board from tilting, which the support force has to hold that up too. What? So when you solve the equations, what do you get for the down force?
72.
72 newtons.
Yes.
And what do you get for the support force?
Still working on it. 752. Someone want to check me?
That's what I got.
72.
That's our answer.
Yay.
Jordan.
I know we just made up the distances for the purposes of this problem, but in like an actual
It would be
example,
given.
you'd be given at least enough so that you
And-
could solve for the other ones, right?
Absolutely. You'd be given all the distances and all the weights. Exactly.
It looks like it's 2.
Yes.
Is it 72?
Pardon?
I didn't get
So I just wanted to check me.
Tommy.
Would there be a question where we'd be given the support force, let's say the down force, and then have to find
Wait, yeah, no, I don't.
the length
Did it in
of
my
the
head.
board or
It's in
something
my head.
from the weight
You could.
Yeah.
or
Me
something?
too.
You could.
Do you guys think we did?
Yep.
I think
770.
752. Or at 752.
So you find FD, and then you
that-
sub that
change-
in.
that
with-
changes
Yeah,
FS.
Like, it can't be over 400.
No.
It has
You
to.
might have left out a number.
1,000. That is some.
Yeah, that makes
The opposite side
sense.
has 480 times 3 meters.
That makes so
It
much
has to be
sense.
over that amount.
Okay, I can't do
Are
it.
these right?
Yeah.
No.
Wait.
FD is, I think it's
I don't know. Wait, one second.
No.
One.
All right. So a correction on the answers. The downward force is 770, and the support force is 1450. All right. Let's look at a second problem. I don't think we're going to be able to solve it, but we might be able to set it up. Okay.
We have 6 minutes. What are you saying we can't solve it?
Hey, you never know.
We have 3 minutes.
This next problem, you have a person standing on a ladder.
How do you how do you
Is someone holding the ladder?
No one's holding the ladder.
That ladder.
Yeah, someone should be
Or
holding.
we're complicated. Because then we have the force of the person holding the ladder.
Robert.
And let's say the person weighs
Thank you.
200 pounds, so 800 newtons. Because he looks like he's very muscular. So
800 newtons for the person. FG of the ladder. Let's say the ladder weighs 50 pounds, so that'd be 200 newtons. We're given some distances down here. 0.70 meters from the base to where the line of action from the person, and we're told from the top of the ladder to the floor right here is 3.8 meters.
Should we draw like F1, F2?
So here's the guy's weight right here. You know what? They don't even have any ladder on this problem, any ladder weight. So you know what? You're probably saying, let's let the ladder be negligible weight. So we're not even going to worry about the weight of the ladder.
Alright, cool. It's a special ladder that doesn't
Right.
actually weigh anything.
Now, when you climb a ladder like this, one thing you're concerned about is the bottom of the ladder sliding out this way. Some people will actually tie a little rope and anchor it to the building like that so it doesn't slide out. Other people put a stake in the ground right there to prevent it from sliding out. Or you could just trust that there's going to be enough friction right there. And basically, that's the friction force right there. That's going to prevent that ladder from sliding out. Here, they're calling it F2.
So that's the friction force?
That's the friction force preventing the bottom of the ladder to slide out. Now, what we're going to try to figure out is what's the minimum or the minimal coefficient of friction, the minimal texture number that will prevent that ladder from sliding out. So, what is the minimum mu sub s needed? force right here, this is how much the floor is holding up on the ladder. They're calling it F1, but what is that normally called?
Normal force.
That's the normal force, so we're going to call that the normal force. And if we want to solve for that coefficient of friction, we know that the force of static friction is equal to u sub s times the norm force, if it's the maximum friction force. So we're going to need this force here, which we're calling F2, and we're going to need this force here, which we're calling F1. If we know F1 and F2, then we can put them in that equation and we can get mu. So one way of getting F1 would be to consider one of the translational equilibrium formulas. Can anyone read your physics teacher's mind what formula I'm talking about? To get F1, the normal force.